So as I said, we're all here to talk about carbon capture. What are the issues, impacts, risks, and potential mitigation? And we are honored to have an esteemed group of experts from across the country here to share their expertise. And each presentation will build on the prior. So the first one will focus on carbon capture and its component parts. What are each process that's involved? And are there differences between different types of carbon capture processes, like those at refineries versus biomass? The second will focus in on the energy and water needs of carbon capture. And the next panel will build off of all of this and discuss the air quality impacts of CCS capture process. So to start, I'm honored to introduce Dr. I can talk louder or? Hello? Okay. So to start, I'm honored to introduce Dr. Meron Tesfaye, Senior Policy Analyst for the Bipartisan Policy Center's Energy Program. And as I said, she will cover the CCS process and the differences between capture at different facility types. So please take it away.
Good morning. Hi, everybody. Are you all able to hear me? Can I get some kind of a flag or a thumbs up? Great. Thank you. Good morning. I'm coming to you from Washington, D.C. And if we can just start off with the first slide, I can quickly introduce one more. Okay, perfect. I'm a senior policy analyst at the Bipartisan Policy Center. We work on bipartisan solutions that can get us to net zero 2050. And we really are wanting some durable solutions that can really deliver on the solution on the climate crisis. Next slide. Ooh. So this is not my most up-to-date slide, but I'll just keep going. Talking about shifting to today's topic, carbon capture ultimately is the key purpose, the technological purpose of carbon capture is to produce high pressure, concentrated stream of CO2 gas. And that capture, first and foremost, will depend on what type of feedstock or source of CO2 we have available. Next, it also depends on the application and the conversion pathway that's used. If you can just click next a couple of times. Yes, thank you. And then the ease of separation from co-products. So whether it is in gaseous form or and mixed with other gases, it will depend on these main aspects. We can move forward, please. And then just keep advancing. Thank you. So when we're talking about feedstock or source, it can be different types of fuel sources, biomass, natural gas, coal, and then how we actually convert those, whether that's thermal process or combustion or thermochemical process. Gasification is a combination of chemical and high temperature process. We can also use biochemical processes to break down biomass. This is mainly used in fuel production. And then whether we apply them for production of fuel or heat, that also determines what kind of carbon capture technology we can apply and the concentration of CO2 we can get. As CO2 is generated, the ease of separation from other co-products, is it pure CO2 that's coming off the stream? Is it produced with water vapor or other liquid products? Or is it solid carbon, which naturally has physical separation capabilities? We can move forward. So when we think about there are a range of carbon capture technologies. So the main three ones are listed here. So I don't have my pointer to show here, but if we're looking at the first process, this is the post-combustion process. You could kind of think think of it being applied to the end of a power production. So you mix your fuel with air, you burn it, and then CO2 is produced along with other gases, and then that is then separated and compressed. Now, pre-combustion is another type of capture technology. It has a few steps prior to that power production step. You can apply gasification and reformation, where you can basically kind of partially oxidize your fuel to produce a higher volume of CO2. And then, your fuel, your hydrogen-rich fuel can then be burned to produce power or heat. The last one, the oxy-fuel combustion, is one of the more recent developments. Here, the modification is actually in the airstream. So if you use an airstream to oxygen and nitrogen, you're able to burn your fuel more effectively and produce a higher concentration of CO2. Next slide, please. You can also use carbon capture in non-power applications, as Dr. Wilcox pointed out. The biomass to fuel production, this is used in bioethanol refineries, generally have a liquid to gas separation because you can in liquid form and separate the CO2. Cement production also also produces CO2, especially in the purification process of limestone. That's a huge source of CO2 that can then be separated. Let's progress one slide forward. So when we go back to these main carbon capture technologies, we can see there are a few differences. Now we're talking here about technical feasibility. If we're thinking about actual feasibility and total life cycle, I think there are other considerations that need to be taken. But for post-combustion process, we're using air. For pre-combustion, we're using a combination of air and steam. And for oxy-fuel, we have a pure oxygen environment. And this can result in different types of CO2 concentration outputs. So the highest of one being in the oxy-fuel combustion, which produces a high volume of CO2. But almost all of them have a pretty high capture potential. So you can capture up to 80, even more than 90% of the CO2 that's produced from these processes. So when we're back up. So when we're thinking about suitability, these for example, a post-combustion process can be really useful for existing or an plant. So these are most power plants in the US, or have a cement facility that is hard to modify, then you can use post-combustion capture pretty effectively. Pre-combustion process, because it has the additional pre-processing gasification capability, is useful. So if you have an IGCC power plant, then you could definitely put it in that system. Ammonia production already has that kind of gasification process, so you can apply it there. And then when we're talking about oxy-fuel combustion, because it has that initial step of separating air, as well as there are burner modifications that make it really effective, it's more suitable for newer plants. So a BECCS power plant has been proposed, and hydrogen to power turbines have also been shown to have really effective use of this capture process. And I'll just stop there, and you can advance to the next slide, and happy to take questions later.
Hello? There we go. Thank you so much, Meron, for sharing. Just a note to everyone in the room that if you do have questions, please write them on the note card and raise your hand. Those will come up to me, and at the end of the 4 presenters, we can get into those questions. But before we jump away from Meron, could you please just explain some of the acronyms that you used in the presentation? For instance, I think it was NGCC and IPCC.
Yes, yes, sorry about that. So that's the natural gas combined cycle. That is we use that for most natural gas power plants. And then IGCC stands for integrated gasification combined cycle. That is also a natural gas system, but it has that the gasification process that I mentioned, which is a kind of a high pressure, high temperature process of partial oxidation prior to combustion.
Thank you so much. So thank you for providing that overview. We have post-combustion, pre-combustion, and oxy-fuel combustion to think about. So next, I'm honored to introduce Dr. Howard Herzog. He's a senior research engineer in the MIT Energy Initiative. Among many accolades and publications, he was a coordinating lead author for the IPCC Special Report on Carbon Dioxide Capture and Storage, published in 2005. Dr. Herzog will take 10 minutes to share with us the energy and water needs of the carbon capture process. Please take it away, and thank you for being here.
Okay, thank you very much. Are my slides up? If you can put my slides up, please.
Yes, they are up.
Oh, I can't see them. Okay. I'm not sure what slide it's on. Anyways, welcome everyone. Nice to see you, at least remotely. I'm a senior research engineer at MIT. I work in the energy initiative there, and I've been working on carbon capture for over 30 years now. When I first got back to MIT a little over 30 years ago, it was a small part of my portfolio, but eventually it took over. And so I've pretty much been involved with almost all aspects of it. Can I have the next slide, please? So I'm going to start here, and this looks at the different way you can categorize feed streams for which you may want to capture CO2 out of. I'm a chemical engineer by training, and probably one of the most important variables to understand and capture is the percent CO2 in your feed stream. Most of the streams we're interested are atmospheric pressure, but there are some high pressure streams, and these high pressure streams are very nice. They're the easiest way to get CO2 out of them, the least energy intensive. If we go down the list here, things become more energy intensive the more dilute we get. These high pressure streams, people mentioned already, some of them ammonia, hydrogen, natural gas processing systems. The high purity streams are also fairly inexpensive because the CO2 has already been concentrated. We talked about just mentioned the oxy-fuel, of course. There is energy use in oxy-fuel because you have to produce the oxygen that you're coming in there. Ethanol plants are another example of a process that pretty much has a pure CO2 stream coming out. Then we get into the dilute, very dilute streams. And this is where the bulk of the interest is for what we want to capture. These are our power plants. These are our cement plants, other industrial things. And now recently people talk about capturing out of the air. I call that extremely dilute. We do capture out of air commercially in spacecrafts and in submarines. And now there's some projects out there. There's some pilots out there that are actually capturing it from the air. Next slide, please. So as I said, the bulk of the processes are dilute or very dilute, and what the main chemical process, the main process for capturing today is post-combustion capture using chemical sorption. Sometimes people call it chemical scrubbing. The process that dominates the market, it uses amines as a sorbent, and You know, when I say post-combustion, we just heard about it, but basically it's exhaust gas cleanup, looking at what's coming out of the tailpipe. And this will be the focus of the next several slides. Next slide, please. Okay, so how much energy does it use? First, to understand the energy use. This chemical scrubbing processes and other processes could also use a combination of energy in terms of both power and heat. And power is generally in the form of electricity, and heat a lot of times is in the form of steam, even though it can be in other, it can be direct heat sometimes. But for the amine process, we have heat and power. The main uses what we need electricity for in the capture process, we have pumps, we have blowers to move our gases and our liquids through the process. We also, at the end, have CO2 come out, which is only at 1 atmosphere. And generally, we need the CO2 compressed up to maybe 100, 150 atmospheres, so we can put it into a pipeline and move it for storage or utilization somewhere. So those both take energy, and you can see numbers here. And then the biggest number is the heat in the chemical process. This breaks chemical bonds. It also provides ways of raising temperatures and changing pressures, sometimes even vacuum pumping, to get this to regenerate the solvent and get a pure CO2 stream. Just one click. So the total work required for these amine processes is about 300 kilowatt hours per ton of CO2. You cannot add up the heat and the electricity numbers. I see people do this all the time, and as a chemical engineer, it just drives me crazy. They aren't equivalent. There is, both of these can be converted into work. Basically, electricity is work, and then the heat is also has a work equivalent. This will vary on how the heat is generated. I'll talk a little more in the next slide, but the total work requirement is approximately 300 kilowatt hours per ton of CO2 for the amine process and a lot of the similar processes. If we want to compare this, a natural gas power plant, for every ton of CO2 going up its exhaust, generates about 2,800 kilowatt hours of electricity. So the use that we're using here is about 10% of that number. Next slide, please. This is sort of summarizes the energy use. The exhaust gas is what I just talked about. And how do we get that heat source there? And in general, at least at power plants, we use cogeneration. Basically, we take the steam out of the steam cycle of the power plant. We take low pressure steam. So steam goes into the steam cycle at high pressure steam. Some of that's used to make electricity. And then the lower pressure steam we can take off and use in our process. And this is the most efficient way of generating it. In direct air capture processes, the one by Climeworks, they published some numbers, and you can see here the power and heat numbers that they work on. And once again, these numbers are higher because it's much more dilute to capture from the air than from exhaust gas. And the total work number you can see here, and that is not the conversion of heat into work is not as efficient here. These numbers are based on using a heat pump to do it. Heat pumps are fairly efficient, but not as efficient as the cogen. The worst thing you can do in terms of efficiency, if you need heat for the process, is just take natural gas or any other fossil fuel, put it in a boiler, and just use that heat coming out directly. That's highly inefficient from a thermodynamic standpoint and an energy use standpoint. Okay. I should say that not all processes use heat. A lot of people are working on processes now for capture that just use all electricity. So these numbers will vary on the exact process, but I just want to give some typical numbers here for us to see that the bulk of the capture works in these areas. Next slide, please. So I'm going to spend the last couple minutes talking about water. I have a reference on here. There's a link to a thesis a student did about 10 years ago that we went into great details on looking at water usage in well, power plants, but also with CCS processes on there. And the bottom line for that is the main use of water in CCS processes is for cooling. So we put energy in. Some of that energy does work for the process, but a lot of the energy goes out as waste heat. And that waste heat generally is taken up by cooling water. Very similar, this is what happens in power plants. When you're looking at the water requirements, you got to look at not just overall water use, but how much is the water withdrawal from your water systems and how much is consumed. So that becomes very important. You can put wet cooling towers in, and this will really lower the withdrawal rates. And in many areas, like for power plants now, do require cooling, but this will also increase water consumption. Dry cooling really minimizes, can almost eliminate both the withdrawals and consumption of water, but that's also very, very expensive. When we look at it, and one of the things we looked at in this thesis is we can see the amount of water needed by carbon capture when you add carbon capture to a power plant really correlates very well with the heat rate. So when you put carbon capture on a power plant, it reduces the plant efficiency because there's more parasitic loads, which then increases the heat rate, and that rate of heat rate increase will also be about the same rate as water increase for that plant. Just say, water, once again, is a very site-specific issue. Whether you want to see more withdrawals or more consumption really depends on the situation you're at, how much water stress you are in the area, what's your water source, can you use, say, ocean water for cooling versus do you have to use other water? One good thing about cooling water, you can use gray water for that. And so let me just wrap up and just say that once again, processes can differ, and the Climeworks process I talked about before actually can use no water and actually generates water. Why is that? Because they put lots of air through the system, so they use air cooling instead of water cooling for the waste heat. And secondly, when they use their amine absorbent, it actually captures CO2 out of the air, 2 molecules of water for every molecule of CO2. So that could actually generate water. I'll stop there and welcome questions.
Thank you so much, Dr. Herzog. We'll be saving questions till after the next panel. But just to summarize, it sounds like the post-combustion process is the most utilized, and that consists of a power and heat stage, then a CO2 separating stage, which includes an amine solution, and then a CO2 compression stage. Dr. Herzog, would you say that I've summarized that sufficiently? Simplified it?
Okay, I say that very quickly again.
A power and heat stage, and then a CO2 separating stage, which includes the amine process, and then a CO2 compression stage.
Yeah, I mean, if you're doing this at a power plant, when you're using an exhaust gas, you have whatever process, whether it's power production or cement production, you take that exhaust gas, you put it into this chemical scrubbing process, this amine process, and that separates the CO2 out. And then the CO2 coming out of that's at atmospheric pressure, and then you compress it up and make it basically liquid-like, so you can then put it into a pipeline and move it to where you may want to store it or use it.
Thank you. Thank you so much. So lastly, I introduced virtually John Thompson, Technology and Markets Director for the Clean Air Task Force, as well as Shaye Wolf, who's here in person, the Climate Science Director with the Center for Biological Diversity's Climate Law Institute. Together, they will discuss the local air quality impacts of the carbon capture technology. And John will begin, followed by Shaye. So please proceed, and thank you, John, for being here.
Well, thank you all for having me. Let me just ask, can you hear me coming through? Just do some kind of indication.
Yes, we can hear you.
Great. All right. Thank you. So what I'd like to do while the slides are coming up is just sort of say a little bit about what I'm going to be covering. We finished a study recently, we haven't published it yet, about looking at the impacts of carbon capture on specific stacks in the cement and refinery interest area. So let's go to the first slide if we could, please. And I'd like to say a little bit about myself and our organization. The Clean Air Task Force is an international environmental group. We're headquartered in Boston. Our European offices are in Brussels. We have about 120 people spread over 14 time zones. I'm based in Illinois, but today I'm traveling, so I'm in Jackson, Mississippi. And our goal is really to decarbonize the global economy and to do so by mid-century. So I'm going to jump to the next slide, please, and talk to you a little bit about the study that I'm going to share some of the, I can't share all the results in 5 minutes, but at least a few. So what we wanted to do was to understand the impact of adding carbon capture to specific smokestacks in a cement and a refinery, to understand what happens to the other air pollutants that are emitted. Do they go up? Do they go down? And there's really reason to think, either one of those could happen. So first of all, to go up, you have more fuel being burned to run the capture equipment, and that releases more emissions. But the absorber also releases, that's used to do the capturing itself, releases some of the amine. We talked about amine earlier in the presentations. That's the chemical that's most commonly used to bind with the CO2 and remove the CO2 gas. So emissions can also go down. In order to use this carbon capture system, you have to take out some of these air pollutants because they interfere with the chemistry of the unit. Dr. Wilcox mentioned that NOx and SO2 are strong acids. Those form heat-stable salts and with the amine. And so if you want to have this run, then you have to clean up some of these emissions beforehand. So what we wanted to do was look at 2 cement stacks, one in California, one in Texas, and the same thing within a refinery, the catalytic cracking unit, one in California and also one in Texas. And the reason we did this is that when we started this study, we noticed a number of things about the published literature. First of all, the published literature tended to make simplifying assumptions about what happens when you put carbon capture on. And they usually do these simplifying assumptions because they're looking at an entire fleet of, say, power plants or refineries or cement plants. And these simplifying assumptions tended to, I think, we were concerned that it oversimplified what actually happens at the plants. So some studies would only put a minimal amount of pretreatment on, a polishing step, sodium hydroxide. Sometimes they would just say, well, we don't know enough about what happens with particulate matter. So we're just going to assume that nothing happens to remove that particulate matter in the absorber. Or we'll make an arbitrary assumption that NOx goes down by 50%. And what we really think is that these are really actually complicated questions. And by looking at specific stacks, we could dig deeper into the actual chemistry, what's going on in some of these examples, and test how much pretreatment you actually need to do to protect this. So if we could go to the next slide, please. Just cover very briefly, what we did is we spent a lot of time collecting data on these specific stacks. Once we had developed the profiles of the emissions and the speciation of this, we turned it over to a consulting firm called Trimeric Corporation. They designed pretreatment. They looked at what the amine capture unit would do. They calculated emissions reductions, and they calculated costs. And then from there, we turned it over to others, SCNA, to do some fence line things, and internally to model health benefits. So this is our paper studies in the sense that we did not build these units, but this is what you would be typically do to design these. So next slide, please. What I wanted to show you is we looked at the Cal Portland plant in Mojave for cement, the Buddha Lehigh plant in cement in Texas, the Martinez facility here in California, and Exxon's Beaumont refinery in Texas. And again, with the refineries, we're looking only at the catalytic cracking units. So what you see in the left is you see the VOCs going up. Those are volatile organic compounds. That's basically coming off the absorber, and that is ammonia. It's VOCs, could be the amine, could be acetaldehyde, could be formaldehyde. And the decreases are in green. So first of all, we modeled 90% capture. We got 87% because we were also capturing auxiliary fuels used to power this equipment. SO2 was virtually eliminated in all of these cases, 99% plus. Particulate matter dropped between 93 and 97.5%. And NOx went down about 2% to as high as 77% or 33%, depending on the refinery. So what I want to do is I want to go to the last slide here, because I know I'm running out of time, and talk to you about what the health impacts of this are. The first column you see are lives saved per year. We ran these through the COBRA model, and for the cement plants, maybe 3 to 6 or more lives saved per year by reducing these emissions of the sulfur, the PM, and the NOx. And we had to do these emission reductions to protect the amine. These weren't done simply to have some kind of environmental benefit, but those particular emissions, the PM, the sulfur, the nitrogen oxides, impact the ability of the amine to work. And so we had to take those out in order to, in our study, in order to get the equipment to work. And those actually lead to a significant reduction in particulate matter, secondary PM. And so you see, for the most part, most of those lives are saved in that small range. Martinez is a higher number. That has to do with just the amount of emissions, but it's also, I think, the COBRA model tends to overstate this. We analyzed the total health benefits of that, anywhere from 27 to $62 million annually. But all of that, say on Mojave or on the refineries, anywhere from say 25 to 55 or 300 to 600, depending, is really valuing the value of a human life. So a lot of other components into this part to deal with, asthma and things like that. But the main contribution is lives saved. And then what you see is the counties that saw the most benefit from that. Now, I should just say that the reason we chose these particular studies is that there's a lot of published literature out there, and I think Shaye's going to share some of that in her presentation. But for the most part, they made simplifying assumptions about what carbon capture does, and it's actually much more complicated. You have to look at specific.
John, we are
stack,
over time. If you want to wrap up for us.
and that's what we did. So thanks, and appreciate your attention today.
Thank you so much. I hope you can hear the applause. I did get a note that we need to ask the online speakers to mute themselves when they're not talking. So if you could please do that, thank you. Lastly, I'm going to introduce Shaye from the Center for Biological Diversity, and then we will jump into questions. Thanks.
Great. How is this microphone working? Okay for folks in the back? No, it seems like not so okay. It's bad. Sorry, can I hold it, hand hold it here? Let's see. All right, how about that for folks in the back? Anybody having trouble? Okay, great. Okay, yeah, hi everyone, I'm Shaye Wolf. I'm the Climate Science Director with the Center for Biological Diversity in Oakland, and I'm going to be talking about the local air quality impacts associated with CCS. So understanding air pollution from CCS really matters because there are big plans for CCS facilities in California communities. So we know of 13 proposed CCS projects in California shown in this map, and all but one are concentrated in Central Valley communities already overburdened with some of the nation's worst air pollution. 8 of those facilities are BECCS or biomass with CCS facilities. Those are shown in turquoise. And what immediately stands out about this issue is how little information there is on a topic that's so crucial for public health, and that there are big claims from some CCS proponents with little evidence. So just to give 2 examples, the Energy Futures Initiative and Stanford report had a key finding that CCS could reduce air pollution emissions, but there are only a few paragraphs in this report on the topic, which ultimately concludes that it requires more analysis and assessment. Similarly, the Lawrence Livermore and DOE report, which promotes an enormous network of BECCS facilities across our state, says that these facilities will reduce air pollution, but there's no assessment of air pollution in that report. So I wanted to first address some common claims about air pollution and CCS, about how CCS could reduce air pollution. And the first is that SO2, sulfur dioxide, and particulate matter must be reduced in the gas stream before CCS treatment with amine solvents. And while this is true, this is just one piece of the pollution picture, as I'll discuss in detail. A second is that if the CCS retrofit is considered a significant modification, it could be subject to current stricter emissions controls or standards. But the retrofit may not be subject to stricter standards, as I can discuss in Q&A, and plus it doesn't mean that pollution is eliminated. So what we do know from research is that local air quality impacts depend on a multitude of factors. First, on the pollutant type, the type of CCS, whether pre-combustion, post-combustion, oxy-fuel combustion, the type of facility, whether refinery or BECCS or a gas-fired power plant. The energy penalty is important, that extra energy needed to run the CCS equipment, which can significantly increase air pollution. There's the CCS life cycle. There's pollution from the facility, from the capture and compression of the CO2 and from the energy penalty. There's pollution at the site of the injection, and there's upstream pollution from the extraction and processing of the fuels needed to run the CCS equipment. The percent of the facility emissions covered by CCS is critical. A refinery has numerous pollution sources and only some stacks may be covered. Pollution control equipment differs among facilities, and we know that that equipment doesn't perform in an idealized way in the real world, right? There are chronic malfunctions, venting and flaring, and facility shutdowns that can increase air pollution. So I'm going to run through some research findings on pollution for common CCS types proposed for California. So as a summary, for BECCS with oxy-fuel combustion CCS, there's almost no information. For BECCS that's bioenergy with CCS, with pre-combustion CCS, there can be increases in PM and SOx. For refineries and gas-fired power plants with post-combustion CCS, there can be increases in PM, NOx, and SOx. So let's start with that first one, BECCS with oxy-fuel combustion. We know that biomass combustion is really polluting. So when you add oxy-fuel combustion CCS to that, a 2013 review found that there is very little information on the criteria air pollutant emissions from that, and that it could produce emissions that have different risks than those currently being managed. There's a really big energy penalty for this technology. So that's at the facility, and we know upstream for BECCS that there's a lot of emissions with, harvesting, cutting, transporting, processing, trucking that material. So for the next category, pre-combustion CCS, this has been proposed for integrated gasification combined cycle power plants, including BECCS. There's similarly very little information and mixed findings for IGCC power plants. SOx, PM, and NOx could increase or decrease. And then this study, a 2022 study on biomass BECCS gasification plants, found that PM emissions increase, it emits more SOx, and there's more pollution-related health harms and mortality. This study, a 2020 study that looked at net zero emissions pathways across California for 2050, said that BECCS comes at a price, as it would emit a considerable amount of air pollutants and reduce health co-benefits by $4 billion. that it emits, biomass combustion emits relatively high levels of air pollution, even though all the BECCS facilities were modeled with emissions control devices to meet emission standards. And importantly, that replacing BECCS with solar and wind emits much less air pollution and reduces mortality. So the figure on the left shows the particulate matter reductions from replacing BECCS with solar and wind. And on the right, that figure shows the avoided deaths. So finally, that post-combustion CCS, this 2019 study looked at the emissions that would come from refineries and gas-fired power plants with and without the CCS technology at three sources: at the facility, shown in blue, upstream, shown in orange, and at the site of injection, shown in pink, and found that NOx increases with that post-combustion CCS at refineries and gas-fired power plants, and particulate matter and SOx similarly increase. So in conclusion, I think the claims of pollutant reductions at CCS facilities are not supported, but rather evidence indicates that air pollution often increases at facilities and upstream, and there are critical information gaps. And this situation seems similar to the fast tracking of fracking without adequate transparency or information on the air pollution and many other health and safety harms. We have dozens of studies about those harms now, so I urge us not to make that same mistake with CCS. Thank you.
Thank you so much. So I have a few questions here, and a lot of them are on the same topic, so I'm going to combine them. One is asking the capture potential that Meron mentioned is 80 to 90%. Is that proven in implemented projects? There's also a question as if, for John Thompson, if the emissions at CCS facilities that have been reduced, is that proven? And then one other question, is there evidence or examples of projects where criteria air pollutants and toxic air contaminants are reduced? Is that proven? So do any of our panelists want to touch on real world kind of proven examples?
Yeah, I mean, I can say something on the capture efficiency. So a lot of the plants have been designed with a 90% nominal capture efficiency, and both the Boundary Dam project and the Petronova project hit that. In fact, I visited Petronova, and they say at times they were doing up to 95% efficiency. So I think that's pretty proven, and a lot of the pilot projects, they've done the same. And the real push now is, at least in terms of the paper research, is figuring out how far you can get this up to 99%. And theoretically, it's possible. It's always a matter of cost on how to do it. But there's been a lot of work recently that suggests you can get up quite a bit above 90 as we, want to get to net zero type emissions. Back, 10, 20 years ago, 90% was a pretty good jump. Now, when we really want to hit net zero, we want to really push the technology up closer to 100%. You'll never get to 100%, but I think in the future, you'll be able to get pretty close.
Let me jump in on the proven question. So there are no catalytic cracking units at refineries that do carbon capture at scale. And that's also true with cement plants. That doesn't mean that you can't do them or that we won't be doing them, but there's been no reason to do it because regulations haven't required them, or we haven't had incentives to do that. Because keep in mind, carbon capture is a pollution control technology at its core. So the only reason that you're going to do it is if you're paid to do it, or if you're forced to do it. Now, in terms of how much can you actually capture, if you want to make ammonia, one of the steps involves separating CO2 from a hydrogen mixture in order to make that ammonia. And generally, these plants do that step at about 99% capture. So if you look back at sort of the commercial usage of carbon capture in industries, beginning in the 1930s, extending through the 1950s and 1960s, there's been a lot of proven industrial applications. What we haven't done until now is really to try to push these into industries where the goal is really to address climate change. So we have limited experience, relatively speaking, on the power sector or in the industrial sector. But it doesn't mean that we can't do that. And what we've learned from those proven experiences is reflected in sort of the information I shared with you. If you want those amine capture units to work, you have to take out the nasties that gum them up. And those particular nasty air pollutants also are the things that harm human health.
I'll just add, yeah, on air pollution in terms of real world examples. I mean, you see the studies that have looked at all of the different sources, facility upstream at the site of injection, that there are a lot of emission sources that need to be taken into account. A lot of places where those will not be captured, or where equipment could malfunction. And I just like to, in terms of real world examples, a lot of the proposals for California are for BECCS facilities and restarting idled biomass plants, many that were shut down because they were polluting communities. And when we looked at we did a Public Records Act request of 18 biomass facility power plants in California and got records of their emission exceedances and violations. And there were lots from 2015 to 2021. I had a figure that I didn't have time to show, but many of those plants were in the range of 30 to 50 exceedances on average per year. Those exceedance could last hours or days. And that's putting pollution, particulate matter, NOx into the community. So that's a real world example of where there are a lot of promises and the equipment is not, not delivering, that the equipment is malfunctioning and communities are getting harmed.
Thank you so much. There's a lot of questions and it's really hard to sift through these. I have one clarifying question. Dr. Herzog, did you say the energy penalty on CCS on natural gas generators is 10%?
No, when you look at a natural gas system, it's about a 15% penalty. I just showed that to sort of compare, give a reference for what the type of power you would need to run an amine process. But when you look at the studies on natural gas, it's about somewhere between 15 and 20% on a coal-fired power plant to somewhere between 20 and 25% of a penalty. Obviously, when you're looking at industrial processes like, say, cement, the energy penalty doesn't make as much sense because you're not producing power at that point. But I just gave that number as a sort of a reference to show the order of magnitude of what the numbers we're talking about.
Thank you. I have a few questions here about the amine process. One is, are there additional emissions from the use of amines for carbon capture? Are there other solvents or sorbents used? And do the different co-pollutants have different effects on the CO2 absorbent? So what is the impact of CO2 absorbent fouling on costs or efficiency?
What was that last part again?
The differences of co-pollutants on CO2 absorbent. So is the impact, I guess, absorbent fouling, what is the impact of that absorbent fouling on costs and efficiency?
Yeah, let me make one quick comment on amine pollution. So there was a fairly intensive study done by the Norwegians a number of years back by their technology center, Mongstad, which is a big test center for amine processes. And they did extensive research. They put out a report that I'm sure is somewhere you can get. And basically, obviously there's never zero pollution, but the amount of pollution was very small. I think it was in parts per billion or maybe even less. And it was well below any health requirement or any dangerous level or any significant level. So that's the only extensive study I know on the amine solvent coming out. Different solvents have different sensitivities to inlet pollution. People looked at ammonia as a solvent a number of years back. It's not as good as amines for a number of reasons, but it does tolerate some of these other pollutants better. Amines are very, very, amines are one of the most finicky sorbents you have in terms of anything getting in there. Particulates make it foam like crazy, which means the process won't work. It will absorb sulfur dioxide and nitrous oxides more strongly than CO2, which basically deactivates the amine, and that's why you want to get it out of there. If you do have sulfur or nitrogen going in there, it will just stick to the amine, and you have to replace the amine eventually. It won't come out in the air.
What we had to do, let me just say what we found in our study was that for many of these stacks, it wasn't sufficient just to do, a sodium hydroxide wash before the absorber. You had to upgrade the particulate matter capture equipment, had to upgrade some other devices, and even it added a lot of extra equipment. The good news, there's a good news, bad news to this. The good news, it reduced emissions significantly. Bad news is that it also increased costs. So that's why it's really important to look at the specific stacks. And in refineries, the catalytic cracking unit has a lot of emissions that would would be very harmful for the amine. And it's the same thing with cement as well.
Thank you. I'll just do two more questions, and I apologize I can't get to them all. One is Kern, LA, and Ventura were identified as top counties benefiting from cement CCS. Why is that, and is there a connection with oil and gas production?
I think you're referring to my slides, and just to be clear, those were having to do largely with the location of those facilities. And because the particulate matter emissions tend to be higher in those counties, when you reduce those emissions, you get the most benefits. So that's why those particular results were the ones that we got.
Thank you. I have one other. We heard a lot in the opening presentation about carbon capture as an almost inevitable climate solution. If carbon capture is really intended to smooth transition off fossil fuels, why do you suppose the fossil fuel industry supports it?
So let me.
Should we instead drive all available resources into renewables?
So a couple of things. The reason you want to do carbon capture, as Dr. Wilcox mentioned, is that we need a lot of different tools for these hard to decarbonize sources. And carbon capture is really a pollution control technology, and it doesn't exist in a vacuum. It's driven by policy. So if your policy is set up that we are moving away from fossil fuels, as California is planning to do, then really what you're doing is not extending the life of fossil fuels by putting pollution controls on refineries. You're just cleaning up the emissions. But there are other policy environments you could construct where that phase out wasn't happening. So I think what's really important is that we focus on the policy on where these technologies are deployed. So what I would hope is that CARB and US EPA would really think hard and long about how that policy is structured, so that what we get is really to net zero, because that's really the main goal. Because at the core of it, this is just a pollution control technology.
I'll say one thing. The getting to net zero will not be easy. I don't know when we'll get there. I hope we do get there at some point, but it is incredibly difficult. We're going to need a lot more than renewables to get to net zero. I'm totally convinced of that. And we really need every arrow in our quiver to really beat this problem. And the goal here, the ultimate goal, is to really stabilize and reduce CO2 and greenhouse gases in the atmosphere. What happens to fossil fuels is a byproduct of it. Now, I know people probably don't like fossil fuels for other reasons, but if you just focused on climate change, how much fossil fuels we use at net zero should be irrelevant. What's really relevant is not putting any greenhouse gases up in the atmosphere.
Yeah, and I'd like to address that too, because I think the question asker hits on a few really good points, is that we really do see the fossil fuel industry and biomass industry promoting CCS. They've gotten billions of dollars in direct money and now a lot of subsidies in public money for this technology that has proven again and again to not live up to, as some other speakers will address, carbon capture promises. When we see carbon capture in the real world of facilities, it's not the 90% that is promised. There's also a lot of air pollution issues that I've talked about. There's a lot of safety issues, and it is not necessary for 1.5 degrees Celsius. The IPCC, once again, in its last report, mapped out pathways for 1.5 that really focus on renewable energy, wind and solar, battery storage, lower energy demand that don't require CCS. So when people say use all the tools in the toolbox, some of those tools help us and some of those tools hurt us. And I think we should focus on the tools that work for everybody, not just somebody.
Can I say something, please? In 2008, I was at the opening of a power plant in Germany, Schwarzepumpe. It was a oxy-fuel demonstration.
Apologies.
Plant, and the
Mixed signal.
company Vattenfall wanted to build a 250 megawatt full-scale unit. The technology was a success. Politics in Germany wouldn't let them. You think Germany would like a nice 250 megawatt low carbon power plant today? What they're doing in Germany and Poland is they're turning up their old coal-fired power plants, putting as much coal as they could to get through the winter so they won't freeze. It's a very complicated problem, and just shouting bromides is not going to get to a solution.
Thank you, thank you. Well, thank you all to our presenters here today. If we can give them a round of applause.